Hey y'all, it's Mr. Boyd back at it again today. Today we're going to be looking at the binomial distribution. As you can see, I've got my handy calculator up on the screen and ready to go. So you're going to need some sort of a graphing calculator today. We're not going to be graphing, but we are going to be using some binomial commands in the calculator, and most scientific calculators don't have that. So if you've downloaded this software that I have, that's great, or if you have your own, a TI-83 or 84 would work just fine as well. Okay, so let's get right into it. Today we're going to be doing the binomial distribution. First, I think I want to talk about when it would be useful and why we need it rather than all the logistics of it. So let's start by talking about the example down here. A fair coin is going to be thrown 10 times. What's the probability that heads is going to come up exactly 6 times? So in this example, if we used what we learned in the previous lesson with discrete random variables, what we would have to do is we'd have to make a table, and we'd have x and the probability of x being x, probability x, and then we'd have to complete this table. And last time we made a tree diagram and we talked about it being thrown 4 times, and that resulted in 16 different branches of the tree. Well, if you throw it 10 times, that's 2 to the 10th different branches. And so what happens is these become undoable questions because they take us hours to figure out, and the organization's horrible and they become too difficult. So that's what the binomial distribution is really for. It's for figuring out these types of questions. Now there are some specific features that we have to understand of them. First of all, it has to be a discrete scenario, meaning you can only take on specific certain values. So like for example, if we're throwing a coin 10 times, the number of heads could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. It couldn't be 9.5. It couldn't be 8.6. So discrete meaning non-continuous, it's only those specific values. The trials have to be independent, which means that for each trial, the probability has to be the same regardless of what happened before. And then we also have to have the probability of success for those trials. So for example, the reason that this is binomial is because we do know what n is. N is 10. So n equals 10 because we're tossing the coin 10 times. The probability of success, and we define that as heads, the probability of heads on any one trial is 1/2, and that probability is unchanging because they're independent events. So as we continue with this, we realize that we do have a binomial distribution. So we have this here. If we flip a coin, what is success? We kind of talked about that. You define it however you want to. Usually it's going to be what we're counting. In this case, we're counting the number of heads, so that's what we're going to define as success. There is a formula for this, and here it is, and it's based on the binomial coefficients that we learned about in Unit 1, and that's right here. All this is saying is there's a bunch of different ways for certain outcomes to happen. Like if you're going to get, in this example, 6 heads, there's many different ways or many different orders you can get that in. Now you're probably not going to have to use this formula because we're probably going to always be able to use the calculator. And there are 2 commands that you need to be aware of in the calculator: binomial PDF and binomial CDF. And here's the difference. PDF is when we're finding an exact or specific case. And while it doesn't actually stand for this, I think of the P as standing for the word particular. As in, we're testing a particular value, like 6 exactly. So here's the example: the probability that exactly 4 students in a selected class have a dog, versus CDF, when we want to test a range of values. So the example, the probability that more than 4 students have a dog. That would be really tricky to do by hand because that leaves open the possibilities that 4 students have, or more than, I guess that would be 5 students have a dog, or 6, or 7, or 8, or 9, all the way up. That's a lot of different calculations. The way I remember this one is I think of the C as standing for cumulative. And when I think that way, that reminds me, oh, it's an accumulation of a bunch of different calculations. So like more than 4, a bunch of different calculations for more than 4. So with that, let's try this example, and let's try a few of the other examples that we're going to have today. So for this one, fair coin is thrown 10 times. The probability that heads will come up exactly 6 times. We've already identified that this is a PDF question. And so now I can go down and I'm going to go in the calculator. I'm going to show you where to go. We need to be on some sort of a calculate screen. You can either open a new document or just go to calculate. I'm going to go to calculate, and let me clear my screen for you. And here I'm going to go into the menu, recognizing that we're doing probability and statistics. It actually occurs in both menus, so it doesn't matter which one you pick. I usually use 5. I don't have a good reason for it, but it's what I use. And then it's the binomial distribution, so we're going to go down to distributions, and then we're going to go to right down in here, and I have binomial PDF and CDF. Let's try PDF. It asked me for the number of trials. We know that's 10. It asked me for the probability of success. That's 1/2. I'm going to put 0.5. And it says the x value is optional. And that's true. If you don't put it in, it'll generate the entire discrete probability table. We don't need that in this case. We want to know a specific probability, so my x value is going to be 6, the number that was asked about in the question. Let's hit enter and see what it is. It looks like that probability is 0.205. So there's my answer. So what did that do? It took something that would have been a really difficult calculation to do by hand, and it made it something that was accessible, quick, and easy. Let's do some more examples now. So we'll talk about the books in the library. In this example, 40% of the books in a library are paperback books. A class checks out 20 of them at random. We want to know the probability that exactly 8 of them are paperbacks. So first of all, that says exactly 8, so that's a PDF. Do we know the number of trials? Sure we do. We're checking out 20 books, and we're doing them randomly. Do we know the probability of success? Well, success is what we're counting. So paperbacks is what we define as success. So the probability of success, if 40% of the books are paperback, that means 0.4. The specific value is 8. So we're going to go in and do the calculation now. And I can go through all the menus if I want, but what I like more is I'm going to click up twice, so that's highlighted. I'm going to bring it down, and I'm going to go edit it. And so we said 20 trials, and the probability now switches to 0.4. And we want to know the probability of getting exactly 8 of them. So 0.1797, that rounds to 0.180. And then what about the next question? The probability that less than 2 are paperbacks. Well, hold on. Less than 2 means that we could have no paperbacks, or we could have 1 paperback. So you see here, this is a little different because we have a range of values. It's a small range, but it is a range of values. And so in this case now, we need to use CDF. Now, it's possible to use PDF once for this one, PDF once for this one, and add the results together, but why would we do that extra work? That doesn't make sense. So let's go do the CDF. So menu, 5, 5, and guys, I'm going pretty quick. I've learned the shortcuts. 5, 5 will get you right into this menu. And then I go to CDF. So what are my number of trials? It's still 20, because the same situation, it's just asking a different question. Probability of success? It's still 0.4. Lower bound? Well, our numbers are here, 0 and 1, so I'm going to use 0. I'm going to leave that alone. We're going to use 1 here, and we're going to see that probability. Seems like it'll be unlikely. And oh my goodness, it is 0.0005. Now, y'all notice, I'm not showing a whole lot of work because with the calculator, there's not a whole lot of work to show. What I'd like you to show is, what's your setup? What function are you using? That way, especially like your teacher, or if I'm your teacher, then I can look at what you're doing and I can figure out what the problem is. I can figure out why you're getting it wrong and give you meaningful feedback. If you don't write anything at all, the only thing a grader has to go off of is your answer right or wrong? And that's not a very good strategy for you. Let's try another one. In this example, we have a basketball player who shoots free throws with 68% success. She needs to make at least 8 out of 10 shots or her coach is going to punish her. Yikes. What's the probability that she will not have to run, that she will not be punished? So let's write down our information. So it gives us a range right here. So right away, I'm going to say, I think this is probably a CDF. Do I know the number of trials? Yeah. She has to make 8 out of 10. That's 10 trials. And do I know the probability of success? Well, if she's a 68% free throw shooter, that's 0.68. And so we've defined success as a made basket now because I've used the percentage that she makes. So now my range, I'm going to go from 8 to 10 because all of those result in her not having the punishment, not having to run. So now we're just ready to type it in. We've laid out all of our groundwork. So here I go. I'm going to go in here and change these numbers. And you can go through the menu if you want, but I like doing it this way, so that's what I'm doing. So 0.4 changes to 0.68. 0 changes to 8 because we want to know what's the probability of her making between 8 and 10 of these shots. And, uh-oh, it's not very good. She's probably running. So 0.331 is her probability, so about a 1 in 3 chance. Okay, and that's how we figure it out. I hope you understand that if we had to do this by hand, it would take a long time and it wouldn't be very pleasant. This is a really, really nice calculator trick. Here's the next thing we got to talk about is expectation in a binomial situation. Okay, now we talked about expectation last time, and we said we'd take each outcome and multiply it by its respective probability. Because we have independent trials in a binomial distribution, the formula is a little bit simplified. But here's the mistake a lot of people make. They go, oh, expectation is always n times p. That's so not true. It's only true if it's binomially distributed. So you have to first identify that. So guys, be really, really careful. And yes, you should write this down, but make a note to yourself. This is only true in the case of a binomial distribution. So let's try these now. In the previous example, what's the expected number of shots she will make? Guys, intuitively, I hope you recognize that if she's a 68% shooter and she's shooting 10 shots, she should probably make 6 or 7. But when we say expectation, we're talking about the long run average of many, many, many iterations of this process. So all we do is we take the number of shots times the probability of making a shot. And that tells us that if we did this every day for a long time, on average, she would come out to 6.8 made baskets. Let's do another one so you can get the hang of it. Here's another one. A fair die is thrown 24 times. We want to know on average how many threes are going to come up. So 24 times, that's n. They asked about threes. They didn't tell us the probability, but if a die is fair and has 6 sides, the probability of a 3 is 1 in 6. So all we have to do is n times p, and I'm taking this right here, y'all. 24 times 1/6, and that's 4. So if you roll the dice 24 times, on average, you're going to get 4 threes. Okay, that's the binomial distribution. Hope you enjoyed it. Hope it made sense, and we'll see you next time.